Yeah, once again, apologies for the delay as we are trying to set up the live stream. So I appreciate your patience as we fix these technical difficulties and get started. So thank you everyone for joining us today, and we will be starting shortly.
I think we can begin the space now. So our live stream has been started on YouTube. So today we will be talking about astrophysics, and our guest is Abhinna Sundar Samantaray. He's a astrophysicist and a PhD student at University of Heidelberg, and his research focus on like multiple stellar populations in star clusters. And he's currently working with Professor Ivake Grebel, who is from University of Heidelberg, and Dr. Holler Baugart, who is from University of Queensland. And his mostly work related to star cluster evolution. Beyond astrophysics, he was also a like teaching assistant, and he's also a Hector Fellow, academic Hector Fellow. So welcome, Abhi. How are you?
I'm good. Thank you for hosting me here. Thank you guys for joining. Can you hear me?
Yeah, we can hear you. So we can start now, I guess.
Yeah, I'm good. I'm ready.
Yeah. So like you completed your BSMS from ISO Mohali, then you moved to Germany for your PhD. So like what was the uh, atmosphere at ISA for research, and what is the like what inspired you to do physics? Like why physics?
I think if you talk about like ICER definitely are like one of the, if not the top, one of the topmost research institutions if you want to do uh, research in any science fields. So in that case, it is good. The atmosphere is good, like it's typically of like any other colleges as well. Very similar structure. But it focuses more on the research. So yes, that definitely boosted my research skills when I was studying at IISER Mohali. And well, it started. Well, if you ask me, like, okay, I wasn't into like all these not physics stuff. I would rather say scientific stuff, like science stuff. I used to enjoy when I was a kid. I used to enjoy all these science stuff and then all these mysteries, puzzles, and everything. But to be honest, it all started with at least space astrophysics wise. It all started with there used to be a show when I was when I think I was in ninth standard to be very precise at the end. And there used to be a show on Net Geo. It used to be called as Cosmos: A Space Time Odyssey. And there used to be more shows like this, like there used to be a show by Morgan Freeman, Into the Wormhole. So all these shows gave me a new concept that I didn't know about like by that time. So it showed me a very new perspective of what's happening in this space. And obviously, universe is full of mysteries. Like it starts with fascination. At least if you're doing astrophysics, it starts with fascination. So everybody would fascinate. Okay, this is so wonderful. This looks so nice. This looks so colorful. Oh my god, this is a black hole. But I think doing research is completely different. Yes, it starts with fascination and you liking the subject, but then ultimately you have to do hardcore research. If you're interested, then yes, do your. I mean, you should join uh, research institutes or at least find a way to do some research if you're really into doing astrophysics or physics research. At least in India, you need a physics degree, and you need to be good at mathematics as well, which I was good at. But then I realized, I should do astrophysics because universe is full of mystery, and I liked all these doing all these things. And definitely isos was one of the places where it boosted, or it at least it gave me a platform to understand physics, to get a degree on physics, and to do all the fundamentals cleared in astrophysics. And then I landed up in Heidelberg because I wanted to do a PhD in astrophysics. So that's how I got here.
Yes, Abhinna. So, what has been kind of that big adjustment, right? Because your undergrad and masters were in India, your PhD is in Germany. What are kind of the cultural differences you see in the approach to research, and how was the transition from masters here to kind of PhD there? Could you give us a brief outline, maybe?
Yes. Yeah. Okay. Honestly, I feel like masters students, what I have, because I also have done some teaching courses. Master students are really good here as well. But people that come from India, or at least who have the basics clear, they are really good. To be honest, Indian masters doing masters in physics, they are really have their fundamentals really tightened up. They are really good in fundamental physics. uh, Astrophysics, maybe it can be competent, but here people are like less mathematical. Like we Indians are really good in mathematics. We know our calculations like within our fingers and everything. We know all the calculation, although it's not mandatory to do it. But here, what I felt is the major difference was the type of research that these guys follow and the atmosphere that they have. I think if you have a good group, then it works really well. The bigger difference I've seen in a few of the younger professors and the group as well in India, but I think the bigger difference is that their working style is completely different. To be honest, like they work from Monday to Friday afternoon. Friday second half is off, and Saturday Sundays they are nobody's working. Whatever you do, it's all on you. Like you want to do research, you do it. If you don't want, you go. Whatever you do, you play, you do sports, you hang out somewhere. It doesn't matter. I think what I felt like is that maybe in some way they are more relaxed whenever they start on Mondays. They are more inclined, they're more focused in their research, and I think the atmosphere is really good. People are really good here. The collaborations here, like across all over Europe, is really really good. And this is actually happening in India as well. Like I've seen a lot of younger professors, they follow this very routine that you probably don't have to work like 24 into 7. It's like you work, there's your lifestyle as well. So that's the difference. But again, like it comes with a lot of other things as well. Like here you won't find food available that easily, so I have to prepare my own food, I have to manage my own lifestyle as well here. But in India, yes, you get a lot of different options as well. If you ask me about the research, I think people are really strong in terms of collaborations here. They work in groups. So, for example, in my case, I need to have two professors, my supervisors from the same institute, and one needs to be from the outside. So it gives you like various opportunities to go and travel around the world and then work with their research groups. And a lot of they host like colloquiums every week. They host a lot of these journal clubs and all these research activities they carry out. Again, it's up to you if you want to join there or not. Let's say somebody's working in extragalactic, somebody's working with compact objects, so you can know what's happening in the other fields as well apart from your own group, which definitely you have your own weekly meetings or something. But yeah.
Yeah, I think that's a great point, and yeah, I definitely think the food thing is one of the harder challenges Indians, I would say. Heidelberg.
Indian food
I'm
is
not.
great. Indian food is
Yeah,
great.
definitely. I think Europe makes you appreciate it all the more. So, what kind of skill sets do you feel it was the difference? Because I think you mentioned, the master students here come with a more mathematical foundation. What is the difference that you find? Because I know astrophysics is a lot of high level mathematics, high level physics, but also kind of
Mhm,
data science, right? So, how
mhm.
do you kind of see this kind of skill set, like at the master's level, between those
Yeah,
in India versus those in Germany?
yeah, that's actually a very good question. So what I found is that the students that I've been teaching a lot, or like who are there in my courses, like that I'm tutoring, I think the very clear difference is that okay, we have our fundamentals very much cleared. Uh, in my case, honestly, I didn't feel that much of a difference because in ISER Mohali, I took like 9 to 10 astrophysics courses, pure astrophysics courses, right? But I know there are a lot of institutions which do not have the same thing, right? So there are, yes, there are opportunities that you can do your courses here, you can take some courses here that you like. But the biggest difference is that, like, I've seen people here and all these universities is that they do their bachelor's thesis on astrophysics and they have really good hands-on. Like, we have our fundamentals really cleared, our theoretical background is really good. But the problem is, whenever you go out, you find people that are really good hands-on, but they might not be good fundamental. They might say, okay, I can do this, and they're very, I would say their niche is very much cleared. For example, I know quantum mechanics, I know classical mechanics, I know, let's say, molecular physics, but they don't need to know everything. Okay, they need to study this, but their expertise is like they know Topcat. They know how I need to use. They are really good in computational because there are courses available that they can do here. There is, let's say, computational astrophysics. They are taught here how to use Topcat, how to use virtual observatory. They are taught here how to use simulations in astrophysics. In astrophysics, okay, I know how to use simulations because I have done a course in ISER Molly, but that was more like uh, what was the course? I forgot. There was one interdisciplinary course that I took at ISMOL. It was more like biology plus something mathematical modeling, something like that. But here it is, the courses are like pure astrophysics. So you have a lot of options here. So if you want to do astrophysics, you can actually take up those courses. Yes, now it is a lot of the courses are available online. So I would say that if you are in bachelor's or master's, one thing definitely you need to have that you need to have good understanding of any of the languages, be it Python, C, C++, whatever you use, because I think now it's pretty normal that everybody knows it. If you know how to use Python or any other language, then it's really good because you cannot say that, okay, I don't know, but I want to do astrophysics, because now it doesn't run that like that. Maybe in some olden days, but now I think it's not. And you need to learn one of these languages, and yes, try your best to do internships, to take up any courses that is available, watch YouTube, whatever you do, but just make sure that you have that fundamental, because at the end it won't matter if you are doing a PhD. I don't care if I don't know quantum mechanics. My field is not that. My field is not quantum mechanics. I need to understand what astrophysics is, what different fields are there inside astrophysics, because okay, I am working with extragalactic, but maybe there is something in solar physics that I don't know. So at least I will have some understanding in those fields as well. But here I have seen like people doing bachelor, like there were a few students who are doing bachelor thesis in, let's say, massive stars. I'm like, okay, bachelors, I didn't know how to like code properly. And these guys are so nice. And these guys don't even know, like, okay, tell me in the integration of this. I know all the integration, I know all the differentiation. They're like, oh no, I'll probably do it online. I can look up all these websites, and I'm like, okay. So I feel like their working style is mostly like smart work. What we do is definitely hard work, but I think we should also, it's time to, switch our smartness and then, take this into our working life and working culture. I think that would really help. Yes, you do hard work, that is absolutely fine, but I think you should know what you want and then try to find a way to just, even if your university doesn't provide those courses, just try to find a way, because I know there are a lot of online courses available. I'm trying my best, at least on LinkedIn or all these stuffs, to share whatever I can. But again, it comes with, like, some time that I have to invest. So sometimes I do it.
Yeah, and I appreciate the effort, because knowledge sharing is the way we can kind of accelerate these things, because the pitfalls that we observe are kind of the learnings that other people need not fall into, right? So I appreciate that. And I think you mentioned that you've worked previously in fields like solar physics and gravitational wave astrophysics as well. So can you kind of give us an introduction to your particular PhD research field? What is it that you're focusing on in stellar astrophysics and kind of, I think, star clusters, as Ayush mentioned? So just
Mhm.
give us maybe an outline on your core research, and maybe give us kind of a beginner's introduction, because a lot of our listeners are very basic astrophysicists, right? They're
Mhm.
space enthusiasts.
Mhm.
So they probably understand things the way you learn from osmosis. So I would appreciate it when break it down to that level and communicate it for our audience. Thank you.
Yeah, sure. So my major goal, at least when my research proposal was made and everything, so I think the major goal was to look for multiple stellar population in star clusters. That is how it was framed initially. So I started with star clusters. So basically, as you all know that star clusters, they have you know stars of the same age, same metallicity, same rotation, everything. So basically, you can fit a single isochrone to the in the CMD to the star cluster. The difference is that at least I think it was like some 1950s or 60s that people started to use or like look into spectroscopy of few of the stars, and they found that there is this anomaly in light element abundance variation, something called like this. So basically, what you can have is like star to star variation. So when you look from one star to other, there are differences in their chemical enrichment. So one star can have like really high carbon enrichment, but it is depleted in oxygen or nitrogen, or high nitrogen or low oxygen. So this was seen spectroscopically. What happened afterwards is that like at least when this photometric instruments really developed, uh, at least in the times when there was HST, the moment HST came, it gave a very refined view of what we see. So first you need to understand is that photometry is basically you are counting photons, right? That is photometry. So photometry is easier than spectroscopy. So when HST looked at the photometric, it sent the first photometric results of the globular clusters, and it started with globular clusters. So what happened was that people started to see. So okay, what happens when you see a CMD of a star cluster? You see your main sequence, you see your red giant branch, you see your main sequence turn-off point, you see horizontal branches and everything, right? So when HST came with its first ever photometric data of the globular clusters, what scientists found was that they could see three main sequences, four main sequences, three red giant branches, or four red giant branches, and all these stuff. And it kept people like confused in a confused state. Okay, why is there when I'm looking into a single star cluster, I should see one main sequence. So basically, if you see one main sequence, one red giant branch, it means that they all follow one single age category. But if you see like four or five main sequences, this means that there are five different ages in the same star cluster. So there are five different stars or like five different population of stars which have five different ages, which actually made no sense initially. But then they looked at these stars which are lying in the different, let's say I'm taking main sequence. So stars lying in these five main sequences, they looked up spectroscopically and they found that they all have the same but different when you see one main sequence to the other. So chemically they were so different, and this is how it started with the theory of multiple stellar population in star clusters. So in star clusters, you have multiple generation of stars. Generation because I'm saying because there is an age gap. So one star, one isochrone is let's say 50 million years. Or well, 50 is like too small. But one, let's say, is 1 gigayear. Second is like 1.5. Third is like 2 gigayears. So you see this 500 million year gap between one generation of the star and the other generation of the star. So this was how it all started. I think last to last decade or something. I think late 90s and early 2000 it started. But then people started
Yeah,
to think, okay, if this is in globular clusters, which is so many stars, and it makes so sense in globular clusters spectroscopically. So you start with photometry, you then verify it using spectroscopy. This is how it is done because spectroscopy is so hard. At least you cannot do spectroscopy for all these stars. It's a bit hard.
of
That's why you
course.
need to have candidates. And and then what people started to think, and it's a very interesting question: is it is this thing that multiple stellar population is only related to globular clusters? Then people started to switch their cameras to the intermediate age star clusters, which is like 1 to 2 giga-year range. And they started to think, okay, if this is there, okay, why globular clusters are so special? There's nothing, there should nothing be special, right? Why not look at intermediate age star clusters? And interestingly, they found the same thing. They found the same exact thing. They found like two main sequences. Main sequence turn-off point got shifted up and down, and then they could see, okay, there is one possible red giant branch or something. Okay, there are three red giant branches. Again, they verified it using spectroscopy. So it made sense. Now, again, the important question is, if it is true for intermediate age clusters, is it possible to look into the younger star clusters and get the same thing? Because understand this, if we actually go into younger star clusters, then we are actually looking into really the formation scenarios of the star cluster. Then we can actually understand how star clusters are formed, or maybe who knows that our theory is completely wrong, how star clusters are formed. What they observed in young star clusters is that there is no like five main sequences or no three main sequences. What they found is that the main sequence is broadened. The main sequence turn-off point is broadened. So what they thought initially is that maybe these broadened main sequences, ultimately, if they star clusters, they age enough, they will split into two, these broadened or three. This was the initial idea. Then people looked into the spectroscopic result, and it was crazy because spectroscopically, when they saw, they found no match, at least what they saw in globular clusters and intermediate clusters. They did not find a match spectroscopically and photometrically. So there was something wrong. There was something off in this theory. Yes, there were some star clusters which did match these observations, but they were like 300, 400 million years aged. But if you look at really young clusters like 50 million years, 60 million years, they just couldn't find one specific reason as to why photometry says there is a broadened main sequence, but spectroscopically, stars are there is not a lot of difference, at least chemically, in when I say chemical enrichment. There was not so much difference. And then the idea comes is that what could be these stars? So this is something that I am researching now. So yes, I started with multiple stellar populations. But then I had to delve into this because if you see a broadened main sequence, there when you try to fit an isochrone, you see okay, one isochrone is not fitting well. So there are some stars which are fastly rotating. Massive stars, B type or O type, and they rotate very fastly. What happens is that because they rotate very fastly, there are a lot of different effects. They get reddened. So what a B or a O type star, let's say a star should be of, let's say, 16th magnitude. Now that magnitude shifts to 16.5 or 17. That's why I'm talking about the B band or the V band, because it rotates so fastly. And because of this rotation, it gets reddened. Basically, it cools down, so it looks cooler. And what again, what happens is that because they rotate very fastly, there is a decretion disk that forms uh, that forms along the stellar equator with from its own material. There is a difference between a decretion and an accretion disk. The accretion disk is formed when the star accretes material from some other star, but the decretion disk is that the star is rotating so fastly that the equator is trying to balance the centrifugal force and the gravitational force. So basically, the star is trying to burst out. So it creates a decretion disk basically from the material which is near the equator, and it creates a disk. This disk actually emits in H alpha and other regimes, which is how it is. These stars are detectable. They are called emission line stars, and these highly rotating stars are the ones which contribute to the main sequence broadening or extended main sequence turn-off points. Right. So this is something that I'm looking into. I am looking into these stars which are called BE stars or OE stars, which are B type stars but have emission. So E smaller e comes from the emission part. So I'm looking into these massive stars which are emitting in different wavelengths, and I'm trying to well uh, trying to answer what could cause these stars to be initially at the first in existence these young star clusters, and then what could give rise to the high rotation speed? Is it something related to the molecular cloud that they were born in, and something like that? So this is something that I'm trying to understand. And overall, if you're
Yeah.
looking star clusters, uh, overall, if you want to look star clusters, they can be studied like either individually if you want to study them. That's absolutely fine. If you are looking into one single star cluster, then you can actually study stellar evolution, stellar nucleosynthesis, or supernova events, or compact objects, binary interactions, and all these. And if you want to look at star clusters as a whole in one single galaxy, then you are looking into more of galaxy evolution stuff, or how these star clusters, they what they how they behave as ensembles there.
Yeah, yeah. I mean, a lot to kind of digest. What I would suggest, Abhinna, is kind of explain a bit more of the jargon. I know, I think your background is
Mhm.
very strong, but I just want to kind of clarify something for the audience. So when you
Mhm.
talk about
Yeah.
isochrones, that means stars that are of the same age, right? Chronology meaning isochrone is at the
Mhm.
same time in the universe.
Mhm.
And HST obviously means the Hubble Space Telescope, I'm assuming, right?
I see. Yeah, yeah.
So yeah. So I'm just, I know
No, no,
all
no.
these are kind of internalized for you, but for our audience, as you're kind of elaborating, I know it's such a complex question, right? Because, for you to have done so much literature and kind of understood this and kind of taking us on the journey, a lot of this is jargon that, works well in the
Mhm.
astrophysics field, but I'll have to kind of open it up a little
Yeah,
more
yeah.
for the audience for sure. So, can you just give us a smaller bit, sir? So I will say, you kind of gave us this kind of giga years and the ages of stars, right? So, can you give
Mhm.
us kind of how does that work? How do you kind of measure the age of stars? And I think you mentioned, I think 50 to 100 million or 500 million, which is the young ones,
Mhm.
right? So can you just run us through just how do stars age and how do you kind of categorize them quickly? And I'll ask you kind of a little bit of individual questions to kind of break down what you just gave
Mhm.
us so that we can digest it a bit more, right?
So by age, you mean like how do I know the age of a star cluster? Is it?
Correct, correct. So you were kind of giving us this whole thing where
Okay.
each
Mhm.
cluster was at different ages, right? You said intermediate age, young, old,
Mhm.
X number of giga
Yeah,
years. So how do you categorize them, and how do you identify, the age of a star? That would be also
yeah.
helpful.
Okay. Yeah, yeah, sure. So, okay, you can feel, any one of you feel free to ask questions in between. So the thing is that you have photons from stars, right? Individual stars. So you get like a number of photons, you get their fluxes, you get their magnitudes at the end, right? You get all the magnitudes. What you do is initially, whatever field you are looking into, you kind of plot something called as an HR diagram, right? So it's a luminosity temperature kind of diagram, or in other sense, it is very similar to how you plot a color magnitude diagram. So by color, I mean magnitude difference of two bands, right? That this gives color and magnitude on the y-axis. So whenever you plot, there would be definitely a scatter plot. What then you do is that you try to fit an isochrone. By isochrone, yes, so basically people have modeled there are different models considering a lot of masses of stars and everything. So at the end, what you get is a single, there are a lot of data points. Definitely you try to fit this line, which has a definite age. Let's say it has, let's say, 1 billion years of age, right? Whatever data points you have, you try to fit based on your assumption. Okay, this might be of this age. And again, you obviously you look into other stuffs as well. For example, I know that my stars, they have a definite profile. The HR diagram has a definite profile. What I mean is that you see main sequence in one particular place. Then you have a red giant branch, basically stars which are much more evolved. Then you see horizontal giant branch. Then you have space for compact objects. Let's say you see white dwarf in some area in that plot. And white dwarf are definitely, they are much more hotter, so they will be on the bluer side of the plot, basically on the hotter side, temperature scale. And they're less luminous, so definitely they will be less luminous, but on the hotter scale. What happens is that whenever you are looking into a star cluster, let's say I have no idea what star cluster I'm looking into. So you see a star cluster, you see, okay, I can see a main sequence, but I don't see a horizontal giant branch, or I don't see a red giant branch. This means there are stars in your star clusters which are not evolved, because you don't see a red giant branch. Then what you do is like, okay, if there are no evolved stars, then I'm assuming that my star clusters is not much evolved, which means that, okay, I can fit, let's say, million years age of isochrone, and that should be good. Million years again is like really, really low level. If you low level, I mean very younger generation. Million years is very, very young. And if you are looking into million, then you can say, okay, I cannot see a red giant branch. This means my stars in these star clusters should be very young. Then I'm trying to fit a younger age line. By younger age line means of isochrone, which is of this many million years of age. Then I'm trying to fit it. Okay, what if you see a red giant branch or horizontal giant branch or asymptotic giant branch? Again, these are different evolutionary stages. If you study stellar evolution, you will understand, okay, depending on the mass of the stars evolve differently. If the star is low, if it's of low mass, then it doesn't evolve really quickly. It rather stays on the main sequence for so long. It might have an age of, let's say, some 1 billion year or maybe 5 billion year, but it still stays on the main sequence. If it is if it is a massive star, then its life cycle or its age is very much limited. Its life is very much limited. It would explode depending on the mass, and then it will get converted to a neutron star or white dwarf, and in extreme cases even a black hole, depending on the mass. And that mass, again, depending on, like, there are a lot of other terms as well, like Chandrasekhar limit and all these stuffs of
Correct.
what
Yeah,
is the
of
minimum
course.
mass and all these stuffs. Again, you don't have to
Exactly.
go into that much detail, but this is
No,
how,
no. I mean,
depending on the
totally.
stellar mass,
So,
stars life
yeah,
is determined.
correct. Understood. So, what are your kind of, when you said, we have to detect and, so I think you mentioned something about a million years. How does the tolerance of this chronological factor go when you kind of measuring the age? And, what are your difficulties in kind of detecting and analyzing these kind of stellar populations or clusters? If that kind of question even makes sense, you know?
Wait, can you repeat again? What?
Yeah. So what I meant is, like, you were talking about this kind of, when you say isochrone, you kind of give this
Mm-hmm,
cluster and isochronic age factor, right? So what is kind of, you said there is
mm-hmm,
kind of some tolerance factor, right? You say give or take a million years, or I don't know, you kind of were
mm-hmm.
saying that.
Yeah.
So how does that kind of tolerance affect your observations? In a sense, what are the kind of the difficulties in estimating or analyzing these kind of clusters and stellar populations when you kind of get
Mm-hmm.
into it?
Yeah. So whenever I get the data, or at least when I started a year back, whenever I used to get the data, I think the bigger problem is that how well I am ready to fit an isochrone. Because at the end, I want to fit an isochrone to get my stellar ages or whatever. Again, to be uh, okay, a 40 million year aged star is not a lot different from a 45 million year aged star. Just to be clear, there is not a lot of difference that happens there, right? Unless it's actually a really massive star, then it evolves very quickly. But otherwise, there's not a lot of difference. The thing is that when you are calculating these magnitudes and everything, you need to take care of something called as extinction, interstellar extinction, right? So the magnitudes, actually what you see, so star, whenever you see a star in the night sky, it appears to be fainter than its actual magnitude because of the interstellar dust in between, which gives it a more red kind of color. So you need to eliminate all those things. That is definitely one thing that one needs to understand whenever they are calculating fluxes or photons or whatever they are doing. These isochrone models, they are mostly okay. I don't work with isochrone models, but people have spent like their entire thesis, 5 years or postdoc sometimes, developing these models. It is more like simulation and observation based, and they tried lot of different models based on nucleosynthesis process. Let's say a star has more carbon. Okay, now it's developing into something more evolutionary, or it is evolving faster depending on its mass. So they have done all these models. The idea or the take home message I would say is that whenever you are doing or whenever you are dealing with all these different, you need to take care of extinction, and second thing is that you need to know if these stars, whatever I'm looking into the cluster, are actual stars or not. Because understand, there could be foreground stars, there could be background stars, but the difference is all these stars in a single star clusters, they have a very similar velocity. They co-move basically. So they will have same radial velocities. They will say have, well, not radial velocity, but they will have same proper motions. So whenever you do this proper motion plot, well, Gaia used to provide so many good kinematics. So proper motion is definitely one way to eliminate those foreground and background stars. You have to make sure that you do not have any foreground or background stars in your data. That is really important, because if you have, then it totally changes your isochrone models and everything. And whenever these people are modeling, they know that okay, I'm assuming that all the stars are from one star cluster. But observationally, whenever you see, okay, whenever I see the small
Understood.
Magellanic Cloud,
So,
I will still see a
an
foreground star.
interesting question comes to me, which is the
Mhm.
idea of dark matter, right? So, dark matter, dark energy is kind of a very non-luminous thing. So, does that do you kind of model it, or does that affect your observations, or more, how you analyze some of these things? Is it part of your research? How does it go?
A dark matter,
Yeah, yeah.
at
So,
least.
I mean, in terms of cosmic evolution and galactic stuff, uh, is there any
Mhm.
part of consideration within your research which focuses on, they say globular clusters of dark matter? Some theories, have suggested that. So, have you kind of factored it into your research? Have you kind of read any literature? Can you give us anything on that? If not, we can move on to the
Mhm.
next question. But just wanted to throw that out there.
Yeah, yeah. So the thing is that, at least based on my understanding and things that I've read, uh, okay. So first of all, you need to understand that where I'm looking. So for example, I'm not looking into globular clusters. So globular clusters are mostly found in the bulge of the galaxy. Let's say I'm taking spiral galaxy. Otherwise, we will find open clusters in the disk of the galaxy, right? Globular clusters are pretty old and they are usually in the bulge of the galaxy. Bulge means the outer part of the galaxy, and the disk is what you see. Bulge is kind of the kind of, how do I explain, like a halo kind of all those stuff there. So globular
The
clusters are
fringe,
usually
right?
find in
The
the,
outer
yeah,
side.
exactly, yeah.
Yeah.
I think a better analogy is like how you see a cycle rim. It's like the rim and all those things are the spiral disk, and the other part, uh, the the or the perpendicular part is kind of the, it goes in all the direction, that is the bulge. So at least based on my understanding, globular clusters seem to have like little or no dark matter, right? And because the thing is, at least the inside part of the globular cluster, the inside part I'm saying, the inside part has really less to play. Okay, maybe on the outside part, because people have observed that, okay, this is all based on what I have read like I think one or two papers. I also thought that initially why there could not be dark matter, at least at least in globular clusters, because if you go into dark matter scenarios, they're mostly, people say the dark matter halo and all those stuff. But if you see the velocities of the stars in the globular cluster, it doesn't change much if you do consider dark matter there or not. So dark matter has a very little play, at least the central part of the globular cluster. So even if you do not take the dark matter into consideration, whether actually, well, in general, we do not take dark matter into consideration because we get really precise velocities. Even if we do not consider, or even if we can, there's no point considering dark matter in the globular clusters as such. But on the outskirts, people have seen like there are velocities difference in some of the stars. They do not move in what we would actually think they would move. But at least in star clusters, I feel like this is again personal opinion. I don't feel like there is a lot of dark matter in at least what I'm studying open clusters. Yes, I do not take consideration of dark matter, but even globular clusters, they might be an effect on the globular clusters. But if they contain dark matter, I think I would still say no.
Okay.
Interesting. So, like, I was wondering, like, what kind of methods or approaches you use to, like, observations, simulations, or statistical models? Like, what kind of models or methods you use for astronomy, like for your research? And like in astronomy, you use lots of programming language and machine learning
Mhm.
stuff. So, like, when a beginner researcher is coming to astrophysics, like, when they have to start this, and can you explain it briefly?
Oh, I didn't get the last part. Sorry. When you have to
Okay,
start it, or
like, okay. So I was asking, like, from the first year, most students don't get these things in college, right? So
yeah.
also most, like, they also don't get do internship in these areas, so they do their own. So like, what are the
Mhm.
some sources you can suggest us?
I think okay, based on my experience, I would say that doing okay, this is again personal experience. I felt like I was getting so less when I was doing coursework compared to what I was getting when I was doing an internship. For example, okay, people might say, okay, you should do coursework, you should have really good theoretical understanding. But I feel like whenever I'm doing internship, I'm anyways reading stuff. I have to read stuff. I have to uh, in order to complete my internship or whatever, at least in first second years, I need to read. I need to read books, or my supervisor would say, okay, read this book. I am studying astrophysics, and I feel like whenever I'm doing internship, I get a more hands-on or real astronomy stuff rather than just fundamental, because most of the courses are pure theoretical, and most of the time I just couldn't relate how the actual data would look like and how will I do it. For example, okay, even if like in my last few years of masters, I remember that the project would be there, and even if I know all the theory, I just don't know the steps to go from 1 to number 10, to go from stage 1 to stage 10. And for that, I need to know the intermediate steps to actually work with real data. And I would suggest that yes, you read books. That is absolutely fine. At least, okay, if you are doing theory, I can understand that you read a lot of books. That is absolutely fine. Uh, but if you are doing observation, I would say yes, read books, but try to get these real data. And there are a lot of archival data. There are a lot of, or try to contact someone who can actually help you with some data, or at least you will have some way to do a project under him, her, whosoever. Maybe if it is not available in your institute, if the project is not available in your institute, try contacting people. I feel that in my first few years I was a bit underconfident, but I was confident enough to write emails to people. I mean, at the end it would be just be, even if there is a rejection, that is still okay to me, because anyways I've not done so much that people will give. But at least it was more about, the more I try, at least my chances of getting selected will be higher. So I would say that, try to go for internships. It not only improves your CV, but at the same time, it gives you a real life experience of how astronomy works. Because studying astronomy or looking into pictures or all these stuff, it feels nice. But at the end, what you need to do for your thesis or for internship or for your PhD is something that is real life data.
So I have a question here,
OA,
Abhinna.
yeah.
Yeah.
Mm-hmm.
I think when you talked about, working with real life data, uh, are there kind of open source data sets and open projects that astronomical observations, we
Mm-hmm.
can kind of work with? Because I remember there's a project by
Mm-hmm.
NASA called Zooniverse, is that it? That kind of gave people, like citizen scientists
Mm-hmm.
contributing on kind of data analysis of astronomical
Yeah, yeah,
data, right? So,
yeah.
what do you think of experience and contributions to that, as kind of real life experience? Because, I totally feel you. Theoretical knowledge can only take you so far as long as, once you apply that knowledge, it becomes so much more tangible to kind of play it off in experience, right? I think
Mm-hmm.
knowing how to apply the knowledge is very crucial to kind of gaining that experience. So I'm not sure if you have worked with it. I think you mentioned you did an internship to get the experience, but what do you think of these kind of open source astronomical data and students kind of taking that up to kind of build their competence and confidence
Mm-hmm.
in
Yes,
astronomy?
yes. These are really good. I think there are a lot of astronomy open source challenges, problems. I think there's something called as international astronomy competition and all these stuff. They do give a lot of experience, and also not even that. I mean, there are a lot of IITs which do that. Okay. I did my. I think I was in like fourth year or something. I think it started with COVID period when I realized I need to learn all these stuffs, and then I found something called as Kritika, as IIT Bombay's astronomy club, and I started with that actually, and they have why okay, maybe I have mentioned it in some of my Twitter pages, and that is a serious knowledgeable thing that you all should, at least the beginner level. It is really good because what do they provide is that there are a set of Jupyter notebooks. So what they do is that they give you problem. Yes, they give you the solution as well, but they ask you, okay, they will give you, let's say, some theory of, or let's say, gravitational wave astrophysics. They will provide the data itself to you, and then they will say, "What? Why don't you try this problem?" They will have answers at the end, but then this gives you an understanding of one particular science problem, one particular astrophysics problem, and then you work on it. And it helps so much because they are covering, I think, 10 to 12 different topics, be it as observation astronomy or some numerical computing or data scraping, web scraping, all these stuff. And similarly, there are a lot of open source uh, these uh, these things available. Uh, I think all these different IITs and I think IIT Kanpur, if I remember correctly, or IIT Indore, they also have these few open pages and all those stuff where you can learn. At least you can start your astronomy experience. That would be really good. I found it really useful, and I would say that was one of the first, not hands-on, but first on coding with astronomy that I did there. I learned my Python in my like third year. It was not like I started like way back. Yes, I was into astronomy. I did a lot of IRAF stuff and everything, mostly reading and all those stuff. But my first on experience was that, and it was so helpful. And not only this, there are other open sources as well. I think um, I'm not sure what that is called. I think it's called Coursera and all those. They also provide, like, have the data and then you try to replicate the problem. Or if you want to go into, or if you are, let's say, independent researcher and if you want to do something else, what you can also do is like look into the research papers of, let's say, some master student or something, or basics, and why don't you replicate the data? Because these students, they definitely work under some supervisors or something. What they do is they try to, whatever they do, they have archival data. So what you do is that data is archival. Basically, the data is public. So you use that data, try to follow the same steps in the research paper or summer project or whatever. Nowadays, summer projects are also public. People put their summer projects, and all these different NCRA, TIF, or all these summer projects are also public. So you can actually see what they have written, what they have done. So the easiest step, okay, if I could go back in past, I would have done that. So try to replicate what they have done. You have the data, you know the steps, they have mentioned the steps. Why don't you try to get a glimpse of what they have done? Because it will give you an experience of handling real life data, because it's completely different. Real HST data and all these data are completely different of what we think, or what at least theory says. It's completely different. Theory says, okay, plot a CMD, but plotting a CMD is some task. So yes, there are some
Yeah,
open sources, but again, at the end, it's mostly like the information, how much information you have, how much information somebody else has.
correct. Yeah.
Yeah, yeah.
So,
So
Down to
like
the
you
information. So yes,
mentioned,
we all should. Yeah, sorry.
yeah, it's like you mentioned coding. So like most of the students like who are not from the ISERS or IIT, they don't have a computer science like course in
Hmm.
their college. So when they do internship, like they had to do with that, they have to learn coding in very they have very few times. So like they use ChatGPT or any other. So like is this
Hmm.
good to
Hmm.
use that? Is this good to use that for astronomy? Like if they don't know coding, like they're just copying and changing the data in that code and doing stuffs. Like does this affect your research career? Like if you don't know much
Well,
coding and using these
see,
LLMs?
personally, I would say that AI, these chat GPT stuff, see, the point is people are using it, but you can use it and you should use it, because this is how everyone is developing, right? Because now it's more about time and saving time and doing your research. But I think there is a line, there is a thin line of, for example, if I want to use chat gpt, I will use it, but at the end I need to, at least I should have basics cleared of what each line of the code says. It's not that I don't know coding. I will just put I just put chat gpt to work. I will say, okay, do this code for me in Jupyter. I'll just copy paste without even understanding what it is doing. Because again, understand this, chat gpt can give wrong answers as well. And okay, AI is developing, but it can give wrong answers. I've tried it now. I use it because, okay, I'll be honest, I use it. When I use it to, let's say, okay, I don't have time to think about all these plots. I say, okay, give me a grid, give me all these text, give me all these text on my plot. Maybe I want my legend to be on the right corner and all these stuff. I don't have time. But again, the thing is, I have done all these things in the past. I have done my coding, basics is cleared. I know, okay, high legend works, but I don't have time right now to put or Google how to put legend on the right side, how to change the font of the legend and everything. Now I can do it. I can just say, Chat GPT, okay, do this for me. Why don't you make a nice plot for me? Why don't you plot this for me and maybe text, or maybe make a circle around that? Because it saves so much time for me. So I would say yes, you should use Chat GPT and everything. And we have seminars and discussions on this as well. We have had it in our institute as well. And most people agreed. At least most of the, and definitely I would say that most of the young scientists, they all agreed, and they all use it. And all these older people that, we don't know how to use Chat GPT, we use Sport and all those stuff. But it saves a lot of time. But I think the main point is, if you're doing something without knowing how it is done, then I think it makes no sense. Yes, you can use Chat GPT for coding. If you don't know how to, how do you label x-axis, what is the first and the second value mean, then yeah, you can learn during that process as well. But I think it becomes a bit tedious, and I think it would take more time to change all those values. And okay, if it is a smaller code, then it's fine. But if it is a bigger code, and if Chat GPT, you know, makes some or a lot of mistake, then your project or whatever, you are going to get wrong results. So for what I do, I ask Chat GPT to do normal stuff. No, why don't you make a plot? Or let's say I will say, okay, no, I want to segregate these values. Please write a code for me. Please segregate the values for me. Please segregate, values above 10,000 temperature and stars less than 10,000 temperature. Please segregate for me. I don't have time. I know how to do it. I can just put a loop and all those stuff, segregate into two arrays, but I don't want to do it because I know you should know the fundamentals. Otherwise, other time you can use chat gpt to answer all your these simple questions, and then you can
Yeah, yeah,
integrate. See, the idea should be yours, but you are just asking ChatGPT to do your steps. But again, you should know step 1, step 2, step 3,
Yeah,
step
you
4,
should know
step
the
5.
logic behind that. Like you should know the
Exactly,
logic behind
exactly.
that.
The logic comes from you, the fundamentals comes from you, but basically you're asking ChatGPT to do your fundamental, all these
Yeah,
things that you have already done in the past.
yeah. So I was looking at your CV. So one of my friends asked question. He's going to join masters. So he asked me like, we have a gap year in your from your masters to PhD. So does that affect your PhD? Like you completed your
No, no, no,
BSMS
no.
in 2020, 2022, I guess, and you started your
Yeah,
PhD in
yeah,
2023. So like, is that
yeah, yeah.
gap year affect your PhD?
That did not. Okay. I mean, when I was telling my story, uh, I did not say some of the things. For example, I was not so initially. Yes, Germany was definitely one of the options, but I got a PhD position in Australia as well. Their visa issues is so terrible right now. Situation is so terrible that people are facing a lot of problems there. The visa thing. That's why I had to switch at some point. Then I found a really nice group, and my supervisor is so nice. And now I do have collaborations in Australia as well. In fact, my co-supervisor was supposed to be my supervisor when I had the offer from Queensland. But then he told me he was helping me out during that visa problem thing. And then I asked him at the end, why don't you join as my co-supervisor? Because you are so nice and everything. And he wasn't, he was really happy that he could supervise me in, well, not supervise, but co-supervise me, but he was really happy. But oh yeah, maybe I forgot your question. What did you ask? Like,
Yeah. So
oh
I asked
sorry,
like, how does
yeah,
a gap year affect to get a
yes, yeah, yeah,
to get a
sorry, yeah, I
PhD
got it. Yeah.
position at
So
any
so
institute?
when I was, yeah, because I graduated from 22, and I did not wait. Like basically, I was doing projects. So I was involved in one of the Kritika projects. I was there, and I was doing one of the projects which was running from my Asar Mohali supervisor. So I think I was doing that as well. And in fact, when I got my PhD position I think I got confirmation, more or less confirmation in March 23. So I had 4 or 5 months gap. So I was thinking, why don't I ask someone to give me a project? Because I'm not doing anything. So I asked people from ESO and everything. And interestingly, in astronomy, it's a really good advantage that you can actually work online. So she asked me that, you can work online, we can have weekly meetings and everything. I'm like, okay, I have like 5 months of doing nothing. I will join you for a project. So the thing is that it's not that I was just sitting at my home doing nothing. I was working on stuff. Even if you have gap year, I would say that try to read, write, or give exam. If you are giving exams, that's completely fine. But at least read. Do not. What I mean is that do not turn off your astrophysics research or physics research in general. Just try to read. Try to email people, try to get something out of, see, the point is that if you do not put in effort, you are going to end up with probably nothing. Yes, you might end up with something nice as well, but I would say put in efforts. And personally, I would say Indian students that come here, they are really young. Gap does not matter. People here or across all over Europe, they do not think that a person has a gap year or something. They mostly will judge you on the basis of the research experience you have and on the experience that you have in the project that is available or that you are going to do under them. That is how they are going to judge you. Like we have here students who are like 35, 36 years, and there is one student or like two students who are like 43, 44. They are even more aged than their supervisor. One of them is like the supervisor is 40, the person who is doing PhD is 45, but it doesn't matter. Indian and I think the Asian people, they are really young who come here. Otherwise, Germans and other European country people, they are like they start off really late. They take their gap year. They enjoy mostly like they will take like 3 years gap doing nothing and then they will start. But I think it is mostly about what experience you have and what experience you have in the project that would be given to you. I think that is important. And at the end, it's mostly about if you are able to explain your gap year, if in case, The thing is that if you want to say that yes, I had problems, I wanted to spend some time alone or doing some research alone, then at least it's fine because you are saying truth. It's not bad. Yes, there are workarounds that you can do. Okay, I was doing this, I was studying for this exam and all those stuff. But I think at the end, this does not matter. No one cares about what age you have, if you have a gap year or something. I think at the end, they look at, okay, this guy has done research on this. If he or she is a good fit into my group, I think that's all what matters. And yes, I think you should always have an answer for your gap year. I mean, yeah, you can say, okay, I was doing all these stuffs, I was doing research on my own, or I was in a part of a research group, or I was doing some internship, or I was doing some pre-doctoral studies, or working as a staff scientist or something like that. I think it's everything is okay. You don't need to like graduate in uh, very recently. That's completely fine. I mean, there are a lot of my friends who graduated in 22, they joined this year. So I don't think gap year actually mattered for them. So I think this should not play in your minds that I have a gap year. Try your best. Try to try your best to explain in your cover letter, in your statement, research statement, what you want to do. Be very clear about what you want to focus on, what research interests you, how is how is the group fits you, or like how you are a good fit to the group, or how you are interested in the research group that your potential supervisor is researching in. It may be master's thesis, it may be internships, it could be PhD project or whatever. I think you should have all your answers ready rather than thinking about, oh, I had a gap year, what should I say, I have nothing to say, all these things.
Yeah, totally true. I think it's always important to kind of be continuously learning, right?
Yeah.
And yeah, I think gap years are totally fine as long as you were using that productively to kind of align with your PhD. And circumstances and life always happen sometimes.
Hmm.
So there's not no harm in being honest there, as
Yeah.
long as you're motivated enough to kind of start the PhD and you have the competency
Hmm.
and skills. All it matters is how confidently you tell
Yeah,
in your
exactly.
kind of
Exactly. I mean,
SOP and things like that. Totally.
in the
Yeah.
interviews and all those stuff, they know kind of from your vibe if you're being honest or not. If you are like just saying, oh no, I did this, they will say, okay, okay, this is fine, but maybe you might, okay, I've seen like a lot of SOPs, and I was actually a part of one of the interview process, and this person goes like, I was like 3 years old, I started looking at this task, I'm like, oh wow, this is something that I want to do. This is, I don't know how to explain this. Okay, if you are if you have done your masters in physics, that means you are interested. If you are applying for a PhD in astrophysics, this means you are interested. You don't have to explain that, I was 2 years, 3 years old, I was looking at the stars and then thought I would be doing astrophysics. No, you don't have to go that far. Come on, like this is not like, but again, like you get like if people don't have, like if they're trying to, bang around the bush, they will do it. But I think they should be very much clear. I think being what I realized here is that you need to be very precise, short, crisp, and honest. I think that all matters. And yes, what you said is right. Confident. Be confident. You don't have to write like 10 pages of something. Write one page, but stick to it. Stick to it. Be confident on yourself. And I think that should be good. And definitely you need to try. If you stop trying, I think, yeah,
Yeah, yeah.
someone
So you
else will
mentioned like
try hard for
you
you.
are you are you reviewed some PhD applications, right? You mentioned like in your talk right now.
Yeah, yeah.
So
I
so
didn't
like
review.
what
I
you
basically,
see,
I was
uh,
there in one of the
yeah,
interview processes.
like what they actually see in your application, like what they actually want in your SOP, uh, in those things, like what they actually looking for.
I think what I understood is that, if you're asking about European application processes, I think here they look mostly for the overlap and the experience of the candidate. They actually do not look at. how much marks this guy has scored in his masters or bachelors, they do not give a shit about it. They don't care. They are like, okay, this guy is doing, okay, let's say this guy is doing star clusters. Okay, I have a project on star clusters. Is this guy a good fit in my group? Then they will interview him or her. They will say, okay, what do you know? What you have done? And I think it worked so nicely here. If you are asking about the US applications, they're a bit tricky because in the US, first year and the second year, you have to do, like, basically you are master student. So you have to attend all the courses and everything. There, marks definitely matters. There they would say, okay, get a 9.9 GPA. I think whatever. I mean, in if you convert it to Indian standards, I think they have like 4 or something. If you don't have a 4, then you don't go into Stanford, Harvard, and all those stuff, MIT. But that actually makes no sense. Like, a good researcher is a good researcher, irrespective of what he has scored in his masters. Like, I've seen people who have like 7 point GPA, but they have 2 or 3 research papers, and 10 out of 10, I will go with them instead of someone who has no publications or something, but has a 10 GPA. Because at the end, here it's more about doing research. It is not about doing courses. I may okay, I may not be a good person in quantum physics. I might have failed in quantum physics, but see, I have 2 publications in astronomy. So why I am not a good fit? Why I am not a good fit in astronomy? Why this person who is more qualified in quantum mechanics, who has scored 100 out of 100 in quantum mechanics, how is he a good fit? So yes, here people judge mostly on the basis of experience that you have. Paper wise, it's kind of a it's kind of a bit gray area. They don't look, or sometimes they also look. If they have two competing applications, they might look into it. But at the end, what I have understood is that no one gives a shit about like how much you have scored in bachelor's or something. Yes, they will look into what courses you have taken and how much you have scored. For example, they will say, okay, astronomy. Oh, he has taken computational astrophysics. Let's see how much he has scored. They don't care. Okay, quantum he has failed. Okay, maybe no, makes no sense. I don't need a quantum guy in my group. So this is something that happened when I was in the interview panel in one of this upcoming Impress applications. So my supervisor asked me to frame few questions for students, and I was asking few of them questions. So at least what I asked to them was like, how do you do research, or how will you approach a research problem? And if you face any difficulty, how are you going to tackle it during your PhD? This is something that I asked. What will you do? Will be your approach if you are stuck somewhere? Because we all will get stuck somewhere, even if it is master's or PhD. What I wanted to ask is like, what will he do? What will she do? That was mostly what I was getting into. Yes, there were a lot of different questions, research based, so I wanted to have some more
Yeah,
in
yeah,
that
yeah.
region.
So like humans like so in India, I guess there is a lot of biasness towards institutes. Like if you're from IIT, if you're from ISRS, you get better chance to select in a program or
Yeah,
internship.
that is unfortunately true. I mean,
Yeah, yeah, right.
to be very honest, I mean, people use ICER, IIT's email IDs, and they write all these. I've graduated from this or that. It does make a difference, but I would say that there are, at least nowadays, there are a lot of opportunities that you can avail, if not in India, but somewhere outside. I think I still think it's a bit hard. Like, why people? I mean, I've seen like people trying to get an internship in India, but again, the major problem is supervisors are like, oh, I don't have money to fund you or something. But I think the best thing that you should, at least people who are in astrophysics, they should take advantage of is that you actually don't need to be there. You don't need to be there on site. You can actually work online as well with weekly meetings. I mean, they don't need to pay you, and you can actually, and if you're trying in here, why don't you try somewhere else? There are a lot of people, there are a lot of postdocs who want to have people doing something for them, and I think it's a really good thing that you can have. I think the good thing is that you should polish your skills, basics, the coding, be it learning, or be it like having fundamentals cleared, I think that this definitely would give you an advantage. But overall, yes. I mean, I will not deny the fact that people from ISERS and IITs, they get an edge over people from other institutes. But I
Yeah,
think
yeah.
I still have seen a lot of people not coming from IITs, not coming from ISERS, but still doing a really, really good job. Real good job.
I think we are heading toward the end of our conversation. I think it crosses 1 hour. So I think we can end now, right?
Okay. Yeah,
Yeah,
that's
thank you
what I
so
was
much,
actually thinking.
Abhinna. Yeah, we'll just have a quick Q&A session. If anyone in the audience and YouTube or anyone has any questions, we will just address them, because I know we are all kind of, it's getting late here. It's been,
Yeah,
I
yeah,
think we had planned this for about
understandable.
60 minutes, and you've given us almost 90. So we're really grateful for you.
Thanks,
I
thanks
think a
so much.
fun little question that I had was to do with kind of if there was kind of a groundbreaking or a myth breaking work that you are doing in part of your research, what exactly would that be? you know uh, if that makes
Groundbreaking
sense.
work.
uh, or
Okay,
universe
okay. So
breaking.
I have, yeah, that's a good question. That's a really good, fun question. So I am planning. This is something that I'm planning to do. So I have some really good number of emission-like stars that have not been observed, and what I'm planning is to, why not name them with initials from in front of the stars. So I'm planning to name them on my name, something like that. So I'm trying to create a catalog where I have really good number of new stars. And my supervisor totally said that feel free to go ahead with that. And she said that you don't have to include anyone, you can just include your name, like Abhi01 or whatever you want to name it. And I've seen people doing that. So she's like, okay, why don't you write your name as well? Like, why don't you name your own stars? Then nobody has observed it, and then if you are observing it, then they're your stars. So I think this is something that I can do. And at some point I felt so nice just by the thought of it, that if it gets published somehow, I will have stars on my name. I will have name on my stars, something like that, something really philosophical. Like I can actually, I don't know, go immortal or something like that. But it's just like fun activity. I mean, but that's just a
Yeah,
part
I
of
mean,
personality. Hopefully,
yeah,
I'll have
that's your
an
legacy, right? Mm.
if someone looks into the small and the large Magellanic clouds and they look into the number of stars, new stars, then definitely my name is going to be there if it is approved by the reviewers and everything. I don't think they will have problems, but again, there are more internal committee and then my co-authors as well. Obviously, I don't think they will have any problems because I've asked them. So, but let's see if it goes through. Then you are definitely going to see some posts about that. It was kind of a dream. Why don't you hear all these stories. Grandma is this star and grandfather is this star. All those stuff. All those. And then I'm like,
So
okay, this is me.
is this something you want to leave for your kids and grandkids? Like, finally your grandkids might say, "Look
Thousands of
there,
me
that is a B01." That's so
thousands of me
nice.
there. No, I might name that these stars on like there are a lot of different. I mean, definitely there are like thousands of stars. I might name on the name of my mother and my sisters or my father. I might name them as well. I
Nice,
mean,
nice,
there's
nice.
no
Can you name a
question.
star?
But just
Like, if in future you discover something like stars or galaxy, can you name after Zetagravit?
yeah, I can. Yeah, I mean, there's no compulsion. I mean, see, the point is that
That
you
would be
can
great.
name whatever you want. If it
Yeah,
is your star, you can just name whatever you can. But I think the initial thing is that sometimes it's like you cannot create a catalog because catalog comes from some telescope. Sometimes you have to write the names of the stars on the basis of what the telescope name or uh,
yeah,
what do you say, the mission name is.
yeah,
So Gaia has its own ID. It's not like Gaia stars are named under someone. It's like ID is this. So it's, I think, the committee who decides at the end. But yeah, I mean, I can do whatever I want, and because
Like I
again, the
have
supervisor
seen
is shown
some
as she just
stars
said.
name. I have seen some names in like code way, like 10555, like this. So they
Yeah,
are
yeah.
very
I
hard
mean,
to
there
remember.
are these M. I think you must have heard about like this M1. These are the names of actual people.
Yeah,
So yeah, I mean, you can M1 all these different objects. So I mean, I've seen people doing that. I think there was a really nice paper. I mean, he's a colleague here, but I've never talked to him because he works at a different institute. So I think you must have heard about this. I think it was called Shiv and Shakti, the the streams in the Milky Way. If I'm not wrong, I have to Google it. I think
Yeah, yeah. No, no, you're right. Yeah,
something
I
like that.
think I've heard.
Yeah,
Yeah,
yeah. So he named
correct.
he named on that. So yeah, yeah. So it's called Shiva and Shakti. Yes, earlier Milky Way's earliest building blocks. Yeah,
Yeah,
and yeah, he was there. I mean, I have seen this guy. I've hardly talked to him. I think I have talked to him like a few times, Khyati. But yeah, he named them and named them. I'm like, yeah, great. That's a really good work. So yeah, if it
yeah.
is your
And
institute, you have to.
yeah. I had a last question for you. Like recently, the
Mhm.
Gaia Gaia was shut down by European Space Agency. So, like, have you ever
Mhm.
worked with data of this instrument?
Yes, yes. Actually, I'm using Gaia's data as well. I'm using Gaia for the field stars and the small and the large Magellanic Clouds. I will be using Gaia for more because see the amount of data is immense. They have so much data, unused data that has not been used or in some sense been used in some practical work. Again, you can come up with a lot of different theories of how you can use the data in your research, but I will be using Gaia's Milky Way kinematical data and then SMC and the LMC. I actually using it for the Magellanic Clouds right now, but in future I will be using it to trace back the individual stars if they actually come from star clusters.
Right,
But
right.
Gaia
So,
is amazing. I
like,
mean, the amount of data and that
yeah,
is the problem. You see, I'm using the very large telescope, the VLT telescope, and the problem is that I found like just to give you numbers, let's say I found like 10,000 stars
yeah. I
and I
heard
found
like,
like 5,000 new stars.
yeah, I
But
heard
then
that
I
there was,
realized that Gaia observed 8,000 of them. So I can only name 2,000 new stars. That's it. So something like
yeah,
that.
I heard that
So
there was
Gaia
more
is like,
than 30,000 scientific publication based on this
yeah, yeah, yeah.
instrument.
Yeah.
Yeah.
I
So
mean,
like,
13,000 scientific publication and more to come. This is like old archival data.
yeah,
And by the way, our institute, the Gaia people are next to the building that we work in, and they are saying the DR4 mission, the Gaia DR4, is going to be launched. I think in some, I think December 2026, November, December 2026. They are planning again. It might go late. It's never earlier. It's again, it's probable date, and it always goes late. So probably in 2027 we should have a new mission as well. So let's see. Let's see if it
like,
works out. Gaia
yeah,
DR3,
like
Gaia
it has
DR4.
cut
Sorry.
down. So, like, where it will orbit? Like, what was the orbit of this instrument in our solar system?
Actually don't know about the actual orbit. I mean, it was
Okay.
definitely there, but what I so basically one of there was, I mean, there was an email which was running in January that guy was going to shut down and that it might observe last night in March, and then I got the email, then I transferred it to the group and everything. But yeah, I mean, it is there in space now. It is going to orbit around the sun. That is for sure.
Yeah.
Not here, but it has left us completely. It is just going to roam. It is going to alone voyage in the cosmic pool, but but yeah, now we are not going to get any data from Gaia. It is going to revolve around the sun, but I mean, yeah, now it's all alone on its own.
Yeah.
uh, yeah. Thank you, Abhinna, for everything. Wanted to ask you, are you part of the Astronomy on Tap in Heidelberg? Have you given any talks there? Have you been to it? Have
Astronomy
you
on.
enjoyed it? So, do you know of this event called Astronomy on Tap, which is a famous thing? So, I've been to one in the Leiden University. So, basically, I think they hold it in a pub, and basically, it's a bunch of people who are space enthusiasts, astronomy enthusiasts. and a lot of
Ah,
PhDs and postdocs come around and discuss the research and kind of it's. I think Leiden used to happen the first Monday of every month, and basically this happened. I know it happens in Heidelberg, so I was wondering if
no, I've
you've
never
heard
been
of
there.
it
I'm
or
looking into it
participated.
right now. No, I'm looking into it.
Okay,
I've never been there. Oh, really?
good,
Thanks,
good.
thanks. I'm not sure.
Sure,
I don't
sure.
know what I'm doing there,
Uh,
but no, we do have colloquiums and everything. It's called high.
Correct.
It should not be
No,
called
this is very
here, but
casual.
it is like high.
Yeah,
Yeah, yeah. No, no,
looks
we
very
have like
casual.
we
Mhm.
no, no, we actually have a lot of different events. So I think the time gets really complicated because I also do sports at the in the evening. So and in the morning it's like I think Monday. Tuesdays is like journal club, and then Wednesdays is like our own group meeting, and then Thursdays is like the Heidelberg Joint Astronomical Colloquium. Uh, and on Fridays is like the our institute's own colloquium. So the week means like just 5 days. So the 5 days are usually packed with something or the other happening. We also have astronomy during coffee breaks and everything. So we have coffee, and then we discuss all these different ideas from different group. People come and they discuss what's happening, what's there, what's new, something else. So we do discuss all these ideas. Uh, but again, it depends on where it is happening and if people are interested. So all these stuff.
Yeah,
But I don't
great to
know.
hear.
Thank you for that.
And
I'll look if it is there somewhere. I might go and
yeah,
join in.
yes, it's called Astronomy on Tap, and I think it's a kind of a global event, which is kind of having local chapters. So
Yeah, yeah.
Heidelberg also has one. I just checked. That's why I was asking if you had heard of it or participated in it. But yeah, I think we're at the end of our space. So I just want to thank our audience for sticking with us today. I want to thank our guest Abhinna for enlightening us with so much, astrophysics. I think I'm now inspired to do a PhD. So it's definitely kind of very inspiring to hear, and definitely, I hope some of your stars get published. I definitely would like to see it. If you do, please do share it with the Zetagravit team. We would love to kind
Yeah,
of
sure, sure.
share it with the world with
Yeah,
you.
we will
So
feature that.
yeah,
Yeah, yeah, no, sure,
definitely.
sure, sure. That is for sure. Yeah.
So
No, but
yeah,
I think the what I feel like doing all these research is I think the knowledge, the difference of how much information you have. I think this is something that we at least our batch and I lagged this information that what's happening at least in my masters. And so I mean nobody would say okay you should apply there, you should apply there, this is the open position, this is something. I think the lack of information holds you back sometimes. It's not like fault of someone, but I think if information if people know something they should at least ideally I would say that they should spread information. Okay, these are the opportunities available, this is something that you should apply, this is something that is there, attend this, participate in this. I think we should all do this because I think it's like whatever you are doing, this event. I think these all really help some sense or the other. I think there are a lot of people who are underconfident or who do not want to ask questions, or like they don't know stuff, or they don't know where where I should start from in astronomy. And I think people, if somewhere or the other, like they should definitely write or blog or like do something at least to help the younger generations.
Yeah, 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 yeah. That's why we are like at Zetagravit. We invite people
Hmm.
like you to to tell about these things and get inspired from people like you, so that they can go in this career.
Yeah, I mean, I should have posted this on LinkedIn as well. I mean, I forgot completely,
no,
Yeah, yeah,
but
no
that's
problem, no problem.
yeah, yeah, but
you
like
can always
I
share
should have. No, no, I
this.
think. Hmm. Yeah, yeah. I mean, if you have, I mean, like this